That's how we'd go through and complete it. So that works. Okay. Because a question really early on came out, did I have to use sodium hydride? What was the role of sodium hydride? It was a base. Are there other bases? That was a good suggestion. LDA. Are there other bases?
Something stupidly strong.
T-butoxide. And your reference there was a phenomenal addition there, Preeti. So let's take a look at that a little bit closer. Would all of these bases have gotten you this product?
Well, I don't think.
No. Why not? T-butoxide gives you the thermodynamic product, or the thermodynamic enolate. That says thermo, which means your enolate, your negative carbon, would have been here, which isn't what we wanted. We wanted all of our chemistry happening out at the kinetic position. Okay. Sodium hydride does that, and LDA would also do that. We color code all our negative signs because they are stupidly strong. Make sense? We good? The last minute and a half has been recorded. So what's drawn up there is all recorded. And me now saying that I've recorded it.
The discerning between the stupidly strong versus the strong there is done because we recognize the fact that we needed the aldehyde, right?
Deciding between strong and stupidly strong is going to be looking at what your product was and deciding where your carbon reacted, where was your carbon attached. So I could still do the aldehyde out at the thermodynamic position. I wouldn't get a condensation. I'd get just an aldol reaction or an aldol-ish reaction without the condensation. Why would I not get a condensation if I went thermodynamic? There's only one alpha hydrogen. So I wouldn't be able to get the full condensation out that side.
So having the pi bond at that 1,4 is a catch-all that you have a condensation.
Having a pi bond form, yes, is your recognition that you have a condensation.
So it's just a mix of an aldol and a michael.
Yeah. So if we want to go through and actually name these, if we look at ultimately what's happening, step one, what are we doing? Acid base, what's the overall kind of chemistry class? That's really vague. That's what I would reference, so I'm glad that at least one of us is on the same wavelength. I would reference in step one, we're running kind of enolate chemistry. Okay. What's happening in step two? That is our nucleophilic addition, kind of our class though. What is the class of chemistry we're doing? Like if step one was acid base and enolate chemistry, what chemistry are we doing in step two? I would argue step two is our aldol. Step three was we had carbon attack the 4 position, right, which is typically classified as, it is again a nucleophilic addition, but you're again getting too mechanistic, which is awesome. You aren't thinking about naming the reactions, but here we're trying to say, well, what's the name reaction equivalent? That would also be correct. That is not the word I was looking for, but that is also correct. Gilman?
No, it's the other one.
Michael addition technically works with this. It's better to reference it as the Gilman. Michael is more in reference to having enolates as your nucleophile. Okay, but it's kind of a Michael, so we can call it Michael-ish, because we've already started that pattern. In step 4, I don't have anything better to call that one. Okay, we might be able to call step 4 enolate. Okay, but that's really more just a substitution, just an SN. Okay, so looking for those patterns, coming up with alternate ways to reference or name that chemistry can help you out when you look at a multiple choice question, because they could say Michael. Well, you have to have a context of what Michael means. Michael's referencing that 1-4 addition. Kind of makes sense? Okay. So we're going to double back and now go kind of fast over this stuff, just because these are kind of big named things. So we went through the enamine very, very quickly. The enamine does act as a 1-4 addition, so it's one of the reasons why we tend to use enamines, is that they don't require the second resonance of an enolate to create a Michael nucleus or a Michael donor, right, to create that nucleophile. They will do a 1-4 addition. The other fancy thing with our enamines, and this goes to show how much time I had when I made the image down below, is that if we go through and make the enamine I think I actually drew that right. Okay, just like with the enolate, we have two possible forms that can come out. Okay, if we want to call it the enamide, like an enolate. If we look at our enolates, we tend to favor the thermodynamic. Why would we favor the thermodynamic? It's more stable. We can force the kinetic. How would I force the kinetic? Okay, that's where I'd have to use my stupidly strong bases. Okay, I know, that's fine. Okay, so we tend to favor thermodynamic, and we would usually use bases like ethoxide or T-butoxide. Okay, if I wanted the kinetic, I'd have to use these stupidly strong things. If I move to the enamine, right? If I use the stupidly strong, what do I get? Stupidly strong favors kinetic. I still get the kinetic. What happens if I switch to just the strong one, like T-butoxide? As in a hint, this is why enamines are neat. Yeah, why are they neat? Interesting. It also forms the kinetic. Okay? That's why enamines are neat and useful. They won't form the thermodynamic product. Okay? Ever. And that seems kind of bizarre because the thermodynamic is more stable. Okay, so why are enamines neat? I can use a weaker base and get the kinetic enolate. Whereas if I was using just the standard enolate form, I have to use a stronger base to get the kinetic. I'm using a stronger thing to get my chemistry to occur, whereas if I just switch it to an enamine, I can use weaker reagents. Okay? Less active reagents is safer. Now I risk my life less in lab. So it makes sense to switch to the enamine. The problem with the enamine is it's kind of like a protecting group. It's not really a protecting group, but it's kind of like that. It protects against the thermodynamic. Well, why would it only form the kinetic? Okay. We can't make an energy argument, okay? At least not obviously, because the energy argument is going to favor thermodynamic. That's why it's called thermodynamic. Thermo for heat, energy. So why is the thermodynamic being disfavored?
The kinetic is irreversible.
Nope, because even with the stupid or just the strong base, it should still be reversible.
Nitrogen's weird like that with its electrons and it wants to...
So we can just blame nitrogen. Nitrogen's just weird. It doesn't. Okay? If that's what gets you to remember it, awesome, fantastic, I accept it. Here's the explanation. Because of the hybridization of that pi system, all of those atoms are roughly in the same plane, which means those hydrogens stack on top of each other. Is it good to have two atoms in the exact same location? No. There's actually a steric repulsion there that causes those two things to move away from each other. If they move away from each other, what happens to the pi overlap in that pi bond? what happens to the pi overlap if that hydrogen goes, get away from me? It breaks the pi overlap. What happens to the pi bond if the pi overlap doesn't exist? It doesn't exist. The thermodynamic doesn't form because there's a steric repulsion that prevents the pi bond from actually forming. Okay? Which is a really neat observation. It's one of the reasons why you see enamine chemistry happen a lot, is because it favors that kinetic result. That's actually what we used in lab. Okay? And that's one of the reasons why we went through using proline as a reagent, because we form an enamine. Okay? So our conjugate additions, they're useful. They make things go a little bit smoother. They get us some easier to make nucleophiles, less stringent chemistry. How do I get rid of the enamine? Yep. Once I've formed the enamine, okay, they're referencing it here as the iminium. Why are they referencing it as the iminium as opposed to the enamine? Because what they're showing is the ketone form of the enolate. Okay, those are related to each other. Those are the tautomers. How would I get rid of the enamine or the imine once it's been formed? Like, I have no idea how this structure right here would become this structure. I wonder if I could move through a reaction. Why can't I protonate it? That would be a phenomenal idea. If I protonate it, yeah, it becomes a good leaving group. What would I replace it with? Probably something with oxygen. What provides oxygen and hydrogens? Water. If I put in an excess of water, what happens to the enamine? I get water hydrolysis, okay, or just hydrolysis, because hydro is referencing water, and I can revert it back to the carbonyl. Okay? This goes back to our nucleophilic additions using weak nucleophiles in chapter 18. Okay? The Robinson annulation, if you combine a Michael addition with an Aldol condensation, it gets a new name, a Robinson annulation. The chemistry is still basically all the same. We have a very acidic hydrogen in that red one. Why is that hydrogen acidic? It's got a lot of resonance. That resonance is revolving around the name of what structure? An enolate. The enolate chemistry is very, very important. That's why that hydrogen is acidic. Why is it super acidic? There are two enolates that can potentially stabilize it. Okay? Which gets me a decent nucleophile as soon as I remove that hydrogen. That nucleophile can now attack an electrophile. What electrophile is it attacking? Okay? It's attacking an alpha-beta unsaturated ketone. Why are alpha-beta unsaturated ketones a little bit more challenging? There are two electrophiles, either at the 2 position or at the 4 position. Where do our enolates attack? That was actually kind of a mean question. Where do our enolates attack? They can do both 1, 2, and 1, 4. But because this is a doubly substituted or a doubly resonance stabilized enolate, it is now a weaker nucleophile, which means it only attacks 1, 4. Because it is now selective for the 1, 4, instead of doing both 1, 2, and 1, 4, when we thought it should have done both, Michael got to stamp probably his name on it.
I thought conjugate addition was 1, 4. So
it is.
He gets to stamp his name on it.
He gets to stamp his name on it because what would we have predicted the enolate to do? Enolate would do 1, 4 and 1, 2.
But it's conjugated.
Only what's conjugated?
Where you have all those numbers there.
Okay. What I'm referencing, Michael gets to stamp his name on it, not because of this structure, but because of this one.
Oh, okay, good.
That structure
Okay, that one.
makes a mess.
No,
That does 1,4 and 1,2.
fair enough.
Because Michael went through and noticed that if I now make it this structure, it only does 1,4. He got to stamp his name to it.
Yeah, but that only does 1,4 because has all that resonance around it and becomes conjugated. So that's not fair.
I'm not arguing fairness there. I agree. I think it's a bit silly to stamp your name on that.
Right.
But that's what's happening.
Because 1,4 is in fact conjugated addition. And
When you're referencing conjugated addition, you're still referencing this structure.
Okay,
That's not the structure that's important. It's this one.
okay.
Okay. Once you've done the Michael addition, if everything is set up nicely, you now have the potential to also do an aldol condensation because we still have acidic hydrogens. Those acidic hydrogens could then theoretically attack the electrophilic carbonyl in what type of a reaction? An aldol condensation. So if I run a Michael addition followed by an aldol condensation, that now gets known as a Robinson annulation. So if you want to complain about Michael getting credit for attaching a name to a stupid reaction, you should be flippin' irritated that Robinson gets to attach a name to it. Right? Just for the record. Fine. I'm not attaching my name to anything. Nope, not happening. We could go through and do a mechanism on this, but you guys went through and piecemealed a mechanism for that quiz, so we're not going to go through and do a mechanism on this. I will say that that may not be a bad thing to ask on exam 3. Do I just need to wait? Is that what's happening? I'm not guaranteeing it. I'm just saying. That's something that we've now said, hey, this is important. We should probably look at it. Are we good? Can we move on? We're good? All good. Yeah? Okay. Which gets us into chapter 20 and chapter 21. We've got roughly 4 weeks to deal with this, maybe 3 weeks. 3 weeks. We had that conversation, right? Actually, now that we're talking about that. Exam 3, did we say was on the Wednesday before Thanksgiving or the Monday? We said Wednesday, right? So we had a little more time? Okay, cool. So we've got today 1, 2, 3, 4, 5 lectures before the next exam. Okay? The next exam, the very first thing it does is nucleophilic addition. Didn't we just have an exam on that? Yes, we did. Okay? The very first part we're going to do is nucleophilic addition. The next part is the nucleophilic elimination. Well, what is an elimination if I compare it to an addition? Directly the opposite. I just want to draw everybody's attention to it. Isn't Mike hilarious? Just pointing that out because I thought that was kind of neat. Okay, so we've seen the eliminations before. When we did our enamine chemistry, those are technically doing a nucleophile elimination. We're forming a pi bond, and we're kicking out a nucleophile. It wasn't supposed to be that fun. Right? So, how could you make that funnier? Like, seriously? So, because we already did a quiz, go ahead and predict the missing product. Okay? So these are now following that new subject, nucleophilic addition followed by elimination. I want you to go through and see what you can predict for each of these. So I can't say everybody messed the first one up, but I'm going to bet most everybody messed the first one up. And of all of these, The very first one, all of you should have gotten right.
I think so.
And then?
There's no and then. It's done.
Why can't it because of the nucleophile?
What happened? It's just an acid-base reaction. There's no nucleophile addition. Why is there no nucleophile addition? What does this species act as? Oh, good job. OH is a nucleophile and a base. What is this functional group? A carboxylic acid. What happens? Acid-base. Once the acid-base reaction happens, we're now left with a neutral result. That conjugate base here is resonance stabilized, making that carbon now not electrophilic. Kills the reaction very, very swiftly. Okay? So carboxylic acids are not susceptible to nucleophilic addition under basic conditions. Okay? So we have to be very, very careful there. 4, just because we're going across, gets a little bit weird. That's your answer. Well, what the heck? What happened to all this structure? The whole point of that giant structure that I just circled is to do what?
Confuse us.
To give you a single nitrogen. What did I just make here? A primary amine. Think back to the substitution reactions we did in chapter 10 with amines. How easy was it to make a primary amine? It was virtually impossible. Okay? If we attempted to make primary amines according to normal substitution reactions, we got a mixture of primary amines, secondary amines, tertiary amines, and quaternary amines. In fact, within that unit, all we said we could do was make quaternary amines and then do an elimination reaction. Okay? So amines were virtually useless. Now I can make a primary amine. Okay? That's known as the Gabriel synthesis. I don't know why that one sticks in my head now. Maybe because I confused the hell out of me at first. But now it makes perfect sense. Don't worry about the mechanism yet. Next one, 2. Right. We have our nitrogen, which could act as a nucleophile. This is the first one that's kind of straightforward. The nucleophile could go through an attack. Okay. There are 2 electrophilic sites, though. Ooh, touche. There are 3 electrophilic sites because we do have an alpha-beta unsaturated carbonyl. Okay. I would make the argument that our nitrogen is probably going to attack here. Okay. Because of a resonance stabilization within that. Okay. Making that electrophilic site slightly less electrophilic. Okay. This is a super, super tricky one, so I wouldn't expect you to know this one all the way through. Okay. And for that matter, remember, I just said this is what I would expect it to do. I actually don't know the answer. Okay, there's our NH3. We'd get the positive. Okay, we're not going to worry about acid-base stuff at this point. The negative comes down to reform our pi bond and ejects a leaving group. The end result. And we're not going to worry about charges. What did you say, Morgan?
Didn't we see on a couple slides ago that nitrogen does 1,4 addition?
Okay, so, and this is one of the things that makes this one unintentionally more difficult. It might do 1,4 addition, but we also aren't looking at just a normal alpha-beta unsaturated carbonyl. Okay, those carbonyls are now more electrophilic because of the resonance of this oxygen. Once that oxygen decides to do resonance one direction, what happens to the other carbon? It becomes even more positive. Okay? So this structure has all sorts of weird things going with it that would make that reaction go entirely sideways. We could predict probably 3 or 4 different things coming out of it. I think 3 different things coming out of it. Okay? All I wanted to do was to drive towards the nucleophilic addition elimination result. Okay? If we look at 3, the answer for 3, no reaction.
That's
Why would there be no reaction? If Br minus comes in and attacks, reforms, one of the things that we might predict is say, hey, well, why does it not go through and form this result? Why can we not get that as a result? And we'll end with this. Br minus versus O minus. Which one's more stable? The Br. Where is Br minus? In solution as a reactant or as a product? As a reactant or as a product? Reactant. If bromide is more stable, it's going to stay as a reactant, which means there's no reaction. I can't produce products because I'm forming something that is more unstable than where I started. So that one ends up coming in as a no reaction. Okay? And then the last one you should theoretically be able to do. Zoop. And we'll leave it at that. Okay? Believe it or not, we will not talk about these on Monday. What we will actually be talking about is nomenclature, acid-base chemistry, and then maybe we'll get into those. Okay? So with that.